students, we have been discussing about this phase diagram and the phase stability. In the last lecture I explained you how we can draw phase PNG composition diagram for isomorphous system, that is the phase diagrams in which you have complete solubility in both in liquid and the solid states. So we are going to move ahead. First thing we will do is take, because we are going to show now immiscibility little bit, first thing we will take again isomorphous systems with a little bit of immiscibility. Okay, immiscibility in the sense not that immiscibility of the phase diagrams. I am following the book of Potter Sterling. This is in the first chapter itself, page number 33. If you have the book, you can clearly follow. So there will be a system with a miscibility gap. So therefore, the first case we are going to discuss is that there is a meeting point of this both the solidus and the liquidus gap. So let me just draw the phase diagram, then it will be clear to you. Suppose this is A, TMA, and this is TMB. Oh, sorry, you have to draw color. So otherwise it's very difficult to follow in a video. Color looks nice. So oops. Okay, and that is what happens. Suppose there is a meeting point of both the solidus and the liquidus somewhere. So how it will look like? Again we will draw the PNG composition diagrams at different temperatures. So first is this is liquid, liquid plus alpha, liquid plus alpha, sorry, you have to put liquid plus beta also, and I am going to draw a miscibility gap. You will also find such a kind of phase diagrams. The alpha phase forms and then it basically transforms into two solution phases, alpha prime and beta. Okay, that's better to write alpha prime and beta because alpha prime may be same phases but different compositions possible, stability range. So how we will draw the phase the composition diagrams? This is at T1, this is at TM A, and this is, let us suppose, at T2. Okay, then I draw it at TMB, and I draw it T3, I draw it at T4. So I have only increased one more temperatures from T1 to T4. So to explain you, obviously all of these diagrams we cannot draw it. So what I will do is I will draw a temperature T1, then I will TMA I have already drawn in the last lecture, so it will be similar. Then I will draw T1, T2, TMB, T3 and T4. So this is at T equal to T1, okay. So this is G versus composition diagram. This is T equal to TMB, T equal to T2, sorry. TMA I am not going to draw. And again this on this side is T equal to T3, T2 I have drawn as TMB, sorry. And then these two will be at T3. T3 is not required to be drawn. T3 is I have already drawn. Okay, let us draw it. And last one will be at T equal to T4. So as you see, there are actually three phases here: liquid, alpha, alpha prime and beta. Okay. So I have to draw all of them, otherwise it will not be clear. So as you see here, liquid has a lower free energy, so it will be at lowest position all through, because this is liquid. And sorry, liquid, I am drawing a different color. Okay. So this is what it is. Then what about the alpha and alpha prime and beta? Okay. This is alpha prime. So there are 4 pages, so they will all be higher. So I will draw it: alpha, beta, oops, beta will be different color. So this is G alpha, this is G beta. Alpha prime and alpha will be similar type, because only thing is stability is different. So whether you draw it at higher or lower temperature does not matter. So let us draw it higher position. So it is very clear that alpha liquid is stable in all the composition range. At T2 you can clearly see that some range alpha is stable, the some range liquid plus alpha is stable, and some range liquid is stable. That means there is a crossover between liquid and alpha. So let us do it quickly. So that is the liquid. So let us first draw the alpha, because alpha is stable on the right side, alpha, and liquid, that is a crossover, and for beta and others there is no point. Oops, sorry, I have drawn it same color, that is the problem. Okay, so this is beta, G alpha, G L, and alpha prime will be somewhere there. So as there is a crossover, so there has to be a common tangent. And this common tangent will demarcate 3 regions: alpha, liquid plus alpha, liquid. That is what you see here. Liquid plus alpha is stable in small composition range, alpha is also liquid stable in large composition on the B region. At T equal to TMB, there is alpha stable in large range, then liquid plus alpha, then liquid, and at the end again alpha, obviously. So therefore it will be little bit different. So how it will be? It will be looking quite interesting. Let us see how we can draw it. So liquid is stable only for a small composition range. So alpha is stable. So let us draw for the alpha. Because alpha is having instability, so therefore, oops, sorry, this it should not be like this. Alpha is stable, then liquid plus alpha liquid. So we should put down little bit, otherwise this will look bad. And liquid crossover, then it's stable. There's another crossover here, and it will meet both there. That's what it will happen. So let me write down, and beta and alpha prime is not of significance. So alpha liquid. So there will be two. You can see there will be two tangents because there are two crossovers. Again, one tangent here, demarcate these two. There's another tangent there. Okay, demarcate. Basically, this will meet here only at this PE end. So that means I have, this is alpha, alpha plus liquid. Then there is a small range in which liquid is stable, and then this is liquid plus alpha, and only at B end alpha is stable. Okay. So that's what it looks like. There are two common tangents between these two curves because two crossovers are there. Now at T3 is very simple, alpha is more stable, so therefore I draw the alpha curves at the bottom, liquid curve will be at the top. Alpha prime beta will be somewhere in between. And beta. So at T4, that's why both alpha prime and beta are stable. That means there has to be crossover between alpha prime and beta. But remember, there will be two crossover because in this range alpha and alpha is stable, then alpha prime and beta is stable, then again alpha is stable. So that's why actually alpha will go through a very interesting things. So first let us finish that liquid. Okay. Liquid is here at the top, no point of discussing of liquid because it is at the top. So now alpha will be very funny, it will pass through such a kind of things because it is unstable, it is undergoing a transformation from alpha to beta plus alpha prime. Okay. So and in the left side it is at equilibrium with alpha prime and beta, so therefore alpha prime and beta will be coming like this. So let us draw for the alpha prime. Yes, alpha is stable, alpha prime, and this is alpha, and beta will also be stable somewhere, but there will be crossover of beta. Okay. So I can draw several common tangents. So obviously most important common tangent is between alpha and beta, and there is a common tangent between alpha prime and beta. Okay, this is beta, and there is a common tangent between alpha and alpha prime. So this will be something like this. Okay, so you can clearly see this is where the alpha is stable, and this is where alpha plus beta prime, alpha prime beta is stable, alpha is stable, and again this side alpha, beyond this alpha is stable. So that's why it says the large composition range alpha plus beta prime is stable. Why the alpha curve goes through such a kind of behavior? Because alpha is undergoing a transformation known as phase separation. So that means in this regime the alpha has this PNG curves will have such a kind of shapes. That means their delta H values are much higher. Please go back to the discussion of the quasi-chemical theory where we have discussed that for a set of parameters the PNG curve of alpha of a particular phase can show miscibility gap, and this is what it is showing. So miscibility gap alpha is clear. This part is a little bit complicated because of the so many crossovers of the PNG curves, but important thing you must remember that it is this PNG of alpha which is behaving in a different manner. It's no longer looks like a typical inverted parabola, but it's initially started inverted parabola, then it goes a high very peak and then again goes back. And this is signature of any kind of phase separations, whether it's a phase separations in the spiral decompositions or any other phase separations. Obviously this will all come back as a part of our exercise in whenever we do that. So the next 8 minutes whatever I have in this lecture, let me just show you what will happen to a eutectic. Obviously this is very little complex, but let me show you eutectic which is much more simple. The reason I show you the very complex thing is that so that you are used to draw the even phase free energy composition diagrams of the systems with a complexity. Now let us look at the eutectic, which all of you know. Eutectic is a reactions, and therefore reactions has to be represented by a horizontal line in the phase diagram. Simple eutectic system with two submineral solutions. Alpha and beta, and with a eutectic reaction, liquid going to alpha plus beta. This is alpha plus beta, sorry, this is alpha plus liquid, not beta, liquid plus beta. Okay, so these are all, this is the simple possible phase diagram. This melting temperature of A, melt temperature of P or B. To make things very simple, let us draw the temperature at which we will draw it. We will draw at only at few temperature. This is the eutectic temperature, it is a reaction. At the eutectic temperature at T equal to TE, we have liquid going to alpha plus beta. This is what is known as eutectic reaction. And then we will draw it at T3. So we are going to draw at T1, T2, T and T3. Others you can try and do yourself. So only at 4 temperatures, G versus composition at T equal to T1, T2, T3, sorry, TE, that's at TE, and at T3. Fine. So, in order to explain you in details, in eutectic reaction, you can have many types of eutectic phase diagram, but this is more general and it is more generic in the sense that you have a solutions at the A reach end, alpha, solutions at the B reach end, beta, because alpha can have some amount of B into A, beta has some amount of A in B, and the solubility drops as a function of temperature. So in C as C, this is solvers. So this goes down as a function of temperature. And in between you have a eutectic reaction. This reaction tells you that liquid is stable till that temperature TE, but below the temperature TE, liquid undergoes transformations leading to formation of alpha and beta together simultaneously. And that is what is basically eutectic reaction. So therefore, actually I have two sets of liquid plus alpha, liquid plus beta, two regimes. We can actually think of this curve as nothing but superimpositions of two isomorphous systems. This is one, that is another one, which I will show you at the end. So let us now draw the free energy composition diagram. So there are, you can see there are 3 phases here, liquid, alpha and beta. So I must have 3 plots in each of this temperature. So first at T1, liquid is stable, so therefore it is very easy. This is liquid, and I draw alpha at higher, basically it should be beta, so okay, alpha and then beta, okay, sorry, this is liquid. So at all compositions, liquid free energy curve is at a lower position, therefore it is more stable. At T2 you can clearly see alpha is stable for some range, then alpha plus liquid, then liquid. That means there is a crossover between alpha and liquid free energy curves, but beta will remain at the top. So I first draw the beta curve, correct, and then I draw alpha and I draw the liquid. It will have a crossover obviously because alpha and liquid are stable at certain composition range, you can see here. So then whenever I have a crossover, I draw a common tangent between them. Very clear, there is no point of discussing again and again. Same thing, liquid has lower positions between alpha is lower and between liquid plus alpha is stable. At the Eutectic temperature, both liquid and alpha and beta, three phases are stable at the temperature. Therefore, they will be having a common tangent. How it is possible? Let us do that. So, first I draw the alpha, first I draw the, we should write down alpha and liquid, otherwise you will not be able to follow up clearly. So, first I draw the alpha. As you see here, alpha is stable here, beta is stable there, these positions. So, therefore, there will be crossover between alpha and liquid here, crossover between beta and liquid there, and at the end, the center, all the three curves will be having common tangent. So, alpha, okay, beta, and liquid, okay, this is GL. So, as you see here, there is a common tangent between 3, common tangent between 3, okay. So that tells me that alpha is stable here, beta is stable there, very clear, this alpha and beta are the lower positions, and in between this liquid plus alpha plus beta are stable because there is a common tangent between of the three curves. That is obvious. At the Eutectic temperature, these three phases must be stable. These three phases must be stable at the Eutectic temperature. That is very clear. That is why all the three curves are actually having a common tangent, and that is why this PNG, the chemical potential of alpha of A in alpha, liquid and beta will be equal here. Similarly, chemical potential of B in alpha, liquid and beta will be equal there. At temperatures T3, again alpha is stable, alpha plus beta and beta. So therefore, crossover between alpha and beta phase diagrams will happen. Liquid will go up, alpha and beta, okay. And there is a crossover, so therefore I need to draw a common tangent again. So that is how actually it will look like for a simple Eutectic system when you have two terminal solutions at presence. And as what the common thing you have learned from this is that if I have to understand the stability of the multiple phases, we have to look at the crossovers of the PNG curves and then draw a common tangent. That is the basic message, a clear basic message you will get from all the discussion for this lecture and the last lecture. And that is why I have not removed this particular diagram, because this is where the basis of whole discussion starts, and we could use this one to explain all kinds of phase diagram and phase transformations. The reason I am drawing all these curves, again I will draw some more in the next class also and go on then move on, to show you that these aspects actually is vital in understanding phase diagram and phase transformations. Okay, so let us stop here and then we will move ahead in the next lecture.